So we introduced the method of characteristics, or the characteristics in the last lecture. So this is kind of the beginning of introducing numerical techniques, right, to solve equations and solve compressible flows, etc. So let us sort of try to understand the concept behind the characteristics, or what exactly the method of characteristics means. Okay, so let me just sort of begin, very simply trying to explain or trying to understand what the concept of this characteristics is, right? And to do that, what we'll do is we'll basically consider the velocity potential equation. Okay, now if you kind of don't remember what the velocity potential equation is, what the potential means, okay, I think you should just go and look up. Just a brief reminder should help. Okay, so just to remind ourselves, so for we'll consider basically solution for an inviscid compressible flow. Okay, now if I consider, say, okay, so the 3D arotational flow. Okay, so in 3D case, velocity potential basically, so if the potential is phi, okay, and I'll just sort of write out the entire 3D equation, right, to kind of just remind ourselves that the complexity of it, or what each term basically means. Okay, so I have this. Right, so this you can see it's pretty engaging, right? But there is a certain pattern to this. Okay, so this is essentially my entire 3D equation. Okay, this is my entire 3D equation, and what we will start with, like I said, to understand the concept of characteristics, is that we'll start with the 2D case. Okay, and let's see if we understand that. So for the 2D case, what we'll do is from here. So this is the entire 3D, say, equation, right? I'll leave that here. So if you see, if I take the 2D case, what we get from here, okay, so this phi x is nothing but this. Okay, this is essentially phi x. So I hope you remember that. So this is essentially phi x and phi y and phi z, etc. Okay, so therefore, if I write it in, so phi x is here, so phi x is nothing but u. Okay, in here, so essentially this is nothing but u square. Okay, this is nothing but u square, and this is nothing but v square. Okay, and in here, so uv. Okay, okay, so then if I write this out, what I get is in 2D is u square by a square. So phi xx is del u del x, isn't it? This term out here is del x of phi x, which is u. Okay, I'll say, let's write it like this, del x of u. Okay, so then what we get here is del u del x, okay, plus, let's get here, so which is 1 minus v square. Okay, and again here, so this is nothing but, again this is nothing but del y of phi y, so which is v. Okay, so if I do that, so this is del v del y, and this is 2d, so we will not have this term here, so we will come back and have this term. So phi x and phi y are u and v respectively, so it is minus 2 uv by a square, and this is basically, if you look at this, it is del y of phi x, right? So this is del y of phi x, which is u. Okay, del y of phi x, del y of phi x, which is u. So therefore, what we have here is del u del y is equal to this. So therefore, this is the equation that we get from here, right? So we have del u del x, we have del v del y, and we have del u del y. Okay. So now let us write this in, let us sort of write an expression for del u del x from here. So what we get is this. So what I get is del u del x, okay, is 2 uv a square del u del y is 1 minus a square. Okay, so we have an expression for this. So let's just sort of take a step back and look what we did. Okay, so what we're trying to do over here, okay, is that we want to numerically solve, okay, the equations which govern our compressible flows. So now this is a velocity. Now we've taken this equation, which is the 3D velocity potential equation. So this is the size or nature of this equation. Okay, if you look at this now, if you so basically we are dealing with, in this particular case, inviscid compressible flow, right? So inviscid compressible flow, right? So in here, so this is the, so the velocity potential equation. So velocity potential is phi. So then this is the 3D equation. So we said we'll sort of start with a 2D equation and then see how we will be able to solve this. Okay. So we were able to get a 2D equation, which is like this, and what I see here is that I can write, say, del u del x in terms of this. So what I essentially need here is del u del y and del v del y, u v, u and v. So if I have these values, then I should be able to get an expression for del u del x. Okay. Now, how do we go ahead and sort of solve this? What is the best way to do that? Now, this is where, you know, CFD comes in. Okay, I'm assuming that you have done at least a basic course in CFD, so you kind of have a little bit of idea about that. So if you don't, I think you have to go back and look at it. Okay, just appraise yourself. You know, just the basics of CFD. Okay. Now, how do we sort of go about this numerically? Okay. Now, for example, let us take a domain. Okay. Now, let us take a domain. We have a fluid flow, and we are trying to calculate, say, del u del x there. Okay. Now, let us take a domain like this. Okay. Okay. So, let us say that okay, and this is, say, the origin, and what we will do is, say, look at this at a particular x location. Okay. So, let us call this as I. So, I guess you know that the indicator in the x direction is I, and in this direction is j. Okay. So, let us look at this xi point, and let us look at this point out here. Okay. So, this point, let us call that as, say, A. Okay. We will call this as A, and this point is, say, I j. Okay. This is at some j and some I. So, say this is y, say, j over here. So, that is the point A, say, I j. Then we will look at, say, these 2 points. So, we have a point here. Okay. So, what this is, say, we will call this as, say, okay. So, let us say we will come here. Okay. We will call this as B, and this is at the same I, but j minus 1. If you look at this, so you have the same I, it is in the same x, but it is at the lower j, which is a lower j. This is y j minus 1, right? This is y j minus 1. So, similarly, so this will be, say, C, and this is I, and is 1 j up, j plus 1. So, say this is basically y j plus 1. Okay. Now, we have these, say we have a domain, we discretize that in a certain way. So, this is essentially, say, delta x, and this is essentially delta y. Okay. So, say we have these 3 points over here. So, now if I, say, need to calculate, for example, okay, now say we need to calculate this. Okay, say we want to calculate u I plus 1 j. Okay, so which is this point? Okay, so this point is, say, I plus 1 j. Okay, so we've got, like, at 1 we've advanced 1 x or 1 delta x in the x direction. Okay, so if I had to, say, calculate that, then let us write this out in, say, the Taylor series. Okay. Okay. If I were to write this, what I will write this as is u I j. This is, I'm writing this in Taylor series. Okay, u I j plus del u del x at I j into delta x, okay, plus the, okay, yeah, so half delta u del x2 at I j del x squared, and so on and so forth. So, this is what we get from Taylor series. So what we see over here is this is essentially our Taylor series, right? And what we see over here is that if I need to get the derivative, say if I need to get, say, u at I plus 1j, then I can write that in terms of the value at a and the derivative of u here, a, right? So if in that case, okay. Now, therefore, in this case, I basically need to calculate del u by del x at, say, this point. Now, if I am able to do that, then I should be able to get, some value over here. Okay. In here. Now, let us do something over here, which I guess you have done in your, like I said, in your CFD classes, in the beginning of CFD classes. Now, if I will ignore the higher order terms over here, okay. If I ignore the higher order terms here, okay, then basically what I will get is my finite difference equations here, okay. So based on that, so what I can do is I can calculate essentially del u del x from here and del u del y, okay, as well as del v del y at this particular point A. Right. Now, there are various like forward difference or backward difference or central difference and so on and so forth. So, you can use those things from those expressions, okay, for and calculate the derivatives at basically this point. So, once you do that, therefore, I can calculate this, I can get an expression for here. So, then once I get these values, so if it is known, then I should be able to calculate del u del x at this particular point. So, this is your basic sort of CFD. Okay. Now, there is a catch here though. Okay. There is a catch. Now, we have chosen this grid, right, in such a way that I am able to use my basic CFD knowledge and and then able to calculate this. There is, however, one catch which I hope you can see from here. Okay, now you can do this as long as this does not go to 0, right. If the denominator goes to 0, then the derivative is also going to blow, right. If this goes to 0, then the derivative will be indeterminate, and it can also be discontinuous. So therefore, there is a condition. Now, what does this derivative, this denominator being 0 mean? Okay, let us look at that. So, the catch here is that this is possible only as long as is not equal to 0. Now, so what happens if it is equal to 0? What happens if this is equal to 0? What you see is that u is equal to a, which means this is sonic. Okay. So, now if there is such a case, okay, if there is such a case, so let us use this say grid itself, okay, and let us take this grid itself and look at this. Now, say this condition happens, you get to a condition when this is 0. Okay. So, that means that, so in here in this grid, okay, so say we have a velocity component, okay, so say we have a velocity, this is the velocity of the fluid, okay, this is the velocity of the fluid. Okay. Now, it so happens that here the x component or u, right, the u here is sonic, which means that this component out here, okay, I have a u component over here, okay, u is equal to a. Okay. So, in that case, Okay. So, in that case the derivatives of u over this particular line. Okay. So, if I have this line say over here and say this is making some angle, okay, say this line out here, okay, this is some line out here and say this is making some angle, okay, let me call that as mu. Okay, let me just call that as mu. So, in here now on this line the derivatives are going to blow. Okay, so, whether it is del u del x or del v del y etcetera, it is going to blow on those on that particular line. Okay. So, now therefore, in this case now if you sort of recall this. So, you have basically a line, okay, you have a line here, right, which makes a certain angle, say in this case which is mu, right, with the flow direction, right, across which the derivatives of the flow are maybe discontinuous and indeterminate. Okay. And the u component is here, the u component is sonic. Okay. So, if you remember this that we have done, we kind of did this a couple of lectures back, that such a line is nothing but a Mach line, right. Such a line is nothing but a Mach line, and so therefore, now in this case, so this line is also called a characteristic line. So, this is sort of introducing the method of characteristics. Okay. So, this is essentially a okay. Now, as you can see here, now this orientation, this x or y, now this does not matter. This does not matter because the thing is, this is the Mach line here. Mach line orientation is basically orientation is with respect to the flow direction, right. So, it makes a certain angle with a mu in such a way that this u out here, okay, the u component is sonic, okay, and therefore, the derivatives across this line, because this u is making a. Now, this is important here. Okay. Now, we have this sonic condition only when this happens, only when we have this condition. So, only when we have such a condition when u is equal to a, okay, and so we have a corresponding line here which is making mu. So, in that case the derivatives across this line are going to blow, okay, and therefore, this is called a characteristic line, and this is physically nothing but a Mach line. Okay. So, yes, and I think if you remember, of course, that right. So, this is something that we did earlier on. Okay. So, having said that, so let us sort of go back and try and see how how we can use this concept. Okay. Okay. So, like we had say this equation here. So, again for the 2D case, right. So, let me sort of write this again. Okay. Okay. So, we had this 2D case. So, we had this equation out here. Okay. So, okay, should I write this again? Okay. So, let me sort of okay. So, we have the 2D equation and we have phi x, right. This is also a function of x and y, right. Phi x is a function of x and y as well as phi y is a function of x and y, right. So, therefore, I can write say d phi x, okay. D phi x is right. So if I can write this, then again, so as we know, as if the phi x is nothing but u, right. So then I can write this as, okay, so I'm going to do this here, and I can also write this as phi xx, and this also I can write as phi xy. Okay. So again similarly, okay, similarly we can write d phi y, right. So this d phi y is nothing but d phi y del x dx. Okay. So then what we have here is phi yx, this is phi yx, which is equal to phi xy. Okay. Now that is the potential condition. So just sort of remind yourselves about that. So then this is phi yy. Okay. So now what we'll do is, so just to bring everything into place, so essentially we say have this equation over here. Okay. We're going to take this, put it there, and we will write this out. Okay. So what we have is, this is what we've got from earlier on. Okay. So what we're going to look at is this expression, this one, and the 2D equation that we've derived before. So let us just sort of write that down. So what we get is 1 minus u square by a square, del u del x is phi xx, okay, minus 2 uv by a square is phi xy plus 1 minus okay. We get this. Now let us look at this equation here. Okay. So what we get here is that okay, so what we get here is let us look here. So what we get is dx, okay, into phi xx, then we get plus dy phi xy, okay, this is equal to du. Okay. Then we look at this equation here, and what we get here is that we get dx phi xy, okay, plus dy right. So this is basically the 2D velocity potential equation, right, and this is what we get from here. Okay. So this is what we get from here. So dx phi xx dy phi xy is equal to du, and this here is again dx phi xy, and dy phi yy is equal to dv. So what you can see is basically we've got a system of simultaneous equations. Okay. Now let us solve for phi xy from here. Okay. Let us solve for phi xy from here. Okay. So we can use Cramer's rule, etc. If I solve for this, what I get is this. Okay. Okay, that, and then we do this, and what we get here is okay. So now this is what we get. Okay. Now, so all we did here, we took the 2D velocity potential equation, combined that with this, and what we are able to get here is this. Okay. So essentially, basically for a given dx and dy, okay, so dx and dy is nothing but, say in this case, the small incremental change in the x direction and y direction respectively. So what we're basically doing here, that for a given dx and dy, we are trying to calculate phi xy. Okay. So now once we have this, so then we use the Cramer's rule to get this. Okay. Now the point is that how are we going to use this? Okay. Now this thing, like we just did just now, okay, now phi xy, okay, phi xy, now this will not blow as long as the denominator is finite. Okay. However, if the denominator goes to 0, right, now if we choose dx and dy in such a way that this denominator goes to 0, then of course we are not going to have a determinate value. We are not going to be able to determine phi xy. We are not going to be able to determine u and a, u, v, etc. Right? If we choose dx and dy in such a way, okay, so that the denominator goes to 0. Okay. So therefore, here what we have seen is that if we have chosen it in such a way that this particular case, right, we have chosen a grid in such a way that in this particular case, okay, the u component becomes sonic, right. Then we have a line which makes mu with it, right, such that u is making u becomes sonic. In that case, the derivatives blow on this particular line, right. So now in here, d cannot be 0, it is physically inconsistent, right. We cannot have a d which is equal to 0. So for this to exist, d has to be finite. Okay. So therefore, now if d however is 0, what we get essentially is the direction of the characteristic lines. Okay. Because if d is 0 out here, then my derivatives are going to blow. So which is the same as what we had discussed out here, right. So if here it becomes a sonic line, then we get these characteristic lines. So let us now look what d is equal to 0 means. Okay. Okay, so now say d is equal to 0. Okay. Now if d is equal to 0, okay, what's okay, so basically, we will, this will go to 0, this determinant is going to go to 0, and what we get here is this. Okay. So I am not going through the total math of this. What we get is this. Okay. So, if d is 0, then what we get is this, right. So, what we are trying to say over here is that if the determinant here, okay, if this goes to 0, then so for a particular chosen dx and dy, right, if my denominator goes to 0, then my derivatives blow, okay, across. So, this happens. So, this is basically this will happen across. So, for a particular value of dx and dy, so those lines are going to be characteristic lines, okay. So, on the characteristic line, so therefore, dy by dx. So, what this is essentially giving us is what this is giving us is basically the orientation, okay, or how we are going to locate these characteristic lines. Okay, so this is what it is giving us. Now, let us see what else information this is giving us. Okay, if you just take a step back and look at this. So, this essentially is nothing but this is, say, total velocity, isn't it? This is, say, v squared. So, what this essentially is equal to, so I can say this is actually equal to m square minus 1, isn't it, Mach number. Okay. Now, if we look at this, so mathematically when you look at this, okay, so if you look at this now just mathematically, so what we have here, okay, is minus uv, okay, let's no need to write this. So, since we have this, okay, now let us look at this conditions here. What we have is that m is greater than 1. Now, these are the case studies. Let us do this. Okay. So, in this particular case, if m is greater than 1, now let us just look at the math of it. If I have m greater than 1, right, what happens? I get 2 real roots, right. I get 2 real roots. Real roots in this case means that I will get dy by dx. Well, what this is essentially giving us is the slope of those characteristic lines. So, I will have 2 characteristic lines. Okay. So, here which means 2 real roots, which means 2 characteristic lines, right. Now, okay, and this physically means that this is a supersonic flow, right. This is a supersonic flow, okay, and what we get in this particular case is a hyperbolic PDE. Okay, what we get here is a what we get here is a hyperbolic PDE. So, mathematically what we get is these 2 real roots, okay, which means this is a hyperbolic PDE. Now, physically what this means is that this corresponds to a supersonic flow, okay, and we are basically looking at 2 characteristic lines here. Okay. Now, let us look at the second case. If, say, m is equal to 1. If we have equal to 1, so we have just 1 real root out here, right. So, if we have is equal to 1, so it is basically it's a so we have essentially 1 real root, okay, mathematically, which means 1 characteristic line. 1 characteristic line, and this is basically a sonic flow. Okay, this is essentially a sonic case, and this corresponds also to mathematically to an elliptic PDE. Okay. Now, if we have the third case, right, if it is subsonic. So, if m is less than 1, you will have imaginary roots. Okay. So, you will have essentially okay, this is sorry, sorry about that. So this is essentially parabolic, right? This is parabolic, and then for subsonic case we will have imaginary roots, right? Imaginary roots, and then this becomes essentially an elliptic PDE, right? An elliptic PDE, and we shall have, so this is basically for subsonic case. Okay, so mathematically that is what we are able to derive from here. So essentially, so the basically the orientation, or so we are now essentially concerned with this, right? So we are essentially concerned with this. So when we are going to solve for supersonic flows, basically we are going to look at hyperbolic PDEs, right, and for supersonic cases, and in this case we are essentially using the characteristics, right, and these characteristics is the orientation of that, or how these are going to be located, these lines, how these are going to be oriented rather in the domain or flow, you know, flow area basically. So is will be given by this. Okay. Now in here, in order to calculate the compatibility equations, okay, which is the, now that we have the pattern, now that we have how the characteristics are going to be located, okay, oriented in the flow field, then how do we now, all we have here is the velocity, definition with respect to the domain. For a given dy by dx, how are the u and v located, etc. Now, what about the properties? How are the properties going to you know, vary along those characteristics or in the flow field? How are we going to collect to that? That is going to be given by the compatibility equations, and we are going to set basically here n is equal to 0 for that. Okay. Now, okay, let us do that and see what we get. Okay, so I am going to sort of erase this over here. Now, we need to discuss this a little more, okay, as to we have set essentially n is equal to 0. So, now in this particular case, so let us first find out the compatibility equations, then we will discuss this a little further, right. Okay. So, let us just put n is equal to 0. Okay. If I do that, then what I get is this. So, what I get is this actually. Okay. Okay. So, now this basically now let's sort of look at this here. So, since I have written that, let us just look at the physical picture of this. Okay. So, if I were to look at the physical, we could sort of go back, it's become a little congested there. Okay. So, say at a particular point, so we have this x and y, right. So, we have this certain domain. So, say at this point, right, A. So, this is our A, and here I have a certain, say, velocity here, right. So, this is the point here. Okay. So, say this at this point, right, at this point we have this velocity, we have this velocity component, right. So, what we found that we are basically going to do dy by dx essentially gives us two characteristic lines. Okay. One, so it gives us the direction of that. So, one we have say like that. So, say this, we are going to call this as a right running characteristic, and let us say look at another one, okay, and say we are going to look at, okay, so this is C minus, right, and as we said, these characteristic lines are essentially Mach lines, right. So, therefore, so if you say look at this, so this is making say positive u, and this is making, say, this is also making u. Okay, the arrows indicate the directions of it, so I didn't write minus u. So this is essentially the orientation of this. Okay, now if let us look at this plot here, and let us look at this. Okay, let us look at this. So now this is, say, theta. Okay, this is the velocity vector there. So say it's making a theta with the horizontal. So this is my, okay, now this is kind of looking like, this is mu. Okay, let's pull that tail down a little bit. Okay, so this tail comes out here. So what I have over here though, say this is dv and this is du. Right, dv du, or u or v. So let's just say, since I have a v over here, so we can just say as u and v. Okay, so essentially what I have over here is a v and we have a u. Okay, and this velocity vector is making an angle theta with the horizontal. If I do that, then what I can write over here, if I look at this picture over here, is that u is equal to v cos theta and v is equal to v sin theta, right? And as we have, of course, this is something that we can see from here as well. Okay, so if I do that, then coming from this particular expression over here, if I look at this, right, and if I can write this as v cos theta and v sin theta, okay, and in here of course we have the sin mu is 1 by m. If I do that, so from this dy by dx can be written dy by dx, right? This I can write actually, okay. So therefore dy by dx, okay, this can be written as tan of tan of theta minus plus mu. Okay, so this is the Mach angle. Okay, so now a question, we'll sort of discuss this a little bit tomorrow. So the question is, are these lines curved or are these lines straight? Okay, what should they be? At least we should know. Okay, so these characteristics essentially. So are these curved, or I've sort of drawn them as curved? Okay, nothing tells us it has to be a straight line. So I drew this curve. So we'll just discuss that a little bit. Okay, or you can kind of see what is happening over here. Okay, so this is essentially that, and so here now if you see dv by d mu, dv by du, if you see from here, if you look at this, okay, here in this case, so what do you with respect to the diagram that we've done here, we can write this also as d theta. Okay, so what essentially is that if I take, say, this is dv, right? Okay, so if I do that, so this is going to be my, so if I take just a small element out there, okay, so therefore this d theta, okay, this is also, so this is equal to minus plus okay, and of course the negative sign, okay, the negative here corresponds to the C minus characteristic, the left running wave, and plus corresponds to C plus corresponding wave. So what you see over here, do you even recognize this equation at all? Now this is, if if you remember this is exactly the same as the Prandtl-Meyer equation, right. This is something that we derived for the Prandtl-Meyer expansion wave. This is exactly equal to that. Okay, so this is exactly similar to that. So therefore, what I can we can write this as, if I now integrate this. Okay, so therefore the Prandtl-Meyer compatibility equations. So in this case, the algebraic compatibility equations, we can write them as like we have done before, I guess. Okay, so I'm just looking for a little bit of space here. So let me say, if I do that. Okay, so it will be, this is say k minus or something, and theta minus oh sorry, yeah, okay, that's correct. So we have a minus plus, so this is on the C minus characteristic. So essentially this corresponds to the left running wave, and this corresponds to this. So therefore these are the compatibility equations for this particular case, for a left running wave and a right running wave. And this is similar to the Raman invariance which we did in the previous lecture. Okay, this is we did J plus and J minus, so this is analogous to that. Okay, so essentially what we will do is we'll kind of discuss this n by d thing a little more tomorrow, now that we've done the math. Okay, we'll go over and understand that a little more in the next lecture. Okay, thanks.